Dispersion modified single mode fibers. As the waveguide contribution DWG depends on the fiber parameters such as the core radius A and the index difference delta, it is possible to design the fiber such that the zero dispersion wavelength is shifted into the neighborhood of 1.55 micrometer. Such fibers are called dispersion shifted fibers. It is also possible to tailor the waveguide contribution such that the total dispersion D is relatively small over a wide wavelength range extending from 1.3 to 1.6 micrometer. Such fibers are called the dispersion flattened fibers. So if we consider the dispersion characteristics for a standard single mode fiber, where we can see that the zero dispersion wavelength is near about 1.3 micrometer range, and this dotted characteristics is actually showing the dispersion flattened fiber, where from 1.3 to 1.6 micrometer the dispersion characteristics is almost flat. At the same time, dispersion is very small and flat, and this is the characteristics of dispersion shifted fiber, where the zero dispersion wavelength is shifted at 1.55 micrometer, where the long haul communication takes place. There are several ways to create dispersion shifted fibers, like we can engineer the refractive index profile of both core and cladding, like triangular profile multiple index design, this one, or segmented core triangular profile design, this one, or dual shaped core design like this one. This will create the zero dispersion wavelength to shift towards the 1.55 micrometer region. So these are some design aspects of dispersion flattened fiber. Here we have double clad fiber, or W fiber. Here, this one is the triple clad fiber, and here we have the quadruple clad fiber. So lots of index profile variation can be done to fabricate dispersion flattened fibers. Dispersion compensating and non-zero dispersion shifted fiber. This figure shows the dispersion characteristics, obviously chromatic dispersion characteristics of standard single mode fiber, non-zero dispersion shifted fiber, and negative dispersion fiber. So this is showing that around 1.3 micrometer for single mode fiber, this is showing the zero dispersion, and it is increasing. For non-zero dispersion shifted fiber, it is the curve is like this, and negative dispersion fiber curve is in the negative portion of the characteristics. Now if we want to compensate the amount of dispersion takes place between transmitter and receiver, what we can do, we have the total dispersion takes place in single mode fiber. Suppose this is the total dispersion, and we use another small section of dispersion compensating fiber. So overall dispersion will be the combination of these two, and it will show that the amount of dispersion for the light wave is very small. That means after having a large length of conventional fiber, we will use small amount of or small length of dispersion compensating fiber, so that overall dispersion of single mode fiber, standard fiber, and the dispersion compensating fiber is nullifies each other, and the overall dispersion becomes zero. This is how we can design dispersion compensating fiber and dispersion shifted fiber, non-zero dispersion shifted fiber. So these are basically just like the previous fibers that we have discussed. We can have lots of variation of refractive indices in core and cladding. So basically that will give us the different kind of fiber, optical fiber, that means dispersion shifted fiber or dispersion compensating fiber, dispersion flattened fiber, etc. Let us have a small numerical problem. A 10 km long fiber produces a overall dispersion of 50 picosecond per nanometer. What will be the length of the dispersion compensating fiber with dispersion minus 1700 picosecond per nanometer kilometer to compensate the overall dispersion? Now, to compensate the total dispersion of the fiber, overall dispersion by a dispersion compensating fiber must be equal and opposite. That means 50 picosecond per nanometer plus minus 1700 picosecond per nanometer kilometer into length of the dispersion compensating fiber, that must be equal to 0. So from that equation we can determine the length of dispersion compensating fiber is 29.4 meter. So obviously the numerical problem, the answer is very easy.